Hello and welcome to the fourth session on Forces in Motion, chapter 10.4 for year 12. So we've had a recap of Newton's second law, F equals ma, force is mass multiplied by acceleration, seen how that relates to weight. So the weight of any object or particle is its mass multiplied by gravitational field strength. So that's some of the stuff we've seen already. Now what we're going to do this session is just link the idea of F equals ma from being just a scalar to vectors. So let's consider force and acceleration as the vectors which they are. So before we get started proper, let's get warmed up with just 4 questions to have a go at. Here they are. So try these on your own, press pause now and just do them in your notes. Press play when you're ready to see how you've done and you can just check your answers against mine. Okay, so without waiting any longer, let's have a look together and do question 1. So we're told here that Phil is rolling a die that is biased. Now some people say rolling a dice, and that's fine, but technically speaking, a dice is a plural word. So you might have 2 or 3 dice. A die is if you only got 1 of them. So a die is just what you might think of as being a dice. It's got numbers 1, 2, 3, 4, 5, 6. However, this one's biased, so the probability of rolling a 6 is 0.2. 1 over 6 is what it normally is if it's unbiased. 1 over 6 is about 0.167. So you're a bit more likely to get a 6 on this biased dice. So for part A, we need to state 3 assumptions that must hold true for this above situation to be modelled as a binomial distribution. So what we're doing here, it's actually a recap from chapter 6 of the stats where we looked at the binomial distribution. There's actually 4 things you could say, 4 assumptions, so you just need any 3 from these following 4. So you could say you need a fixed number of trials. The trials need to be independent of each other. There's only 2 possible outcomes, so in this case you can think of it as either being a 6 or not a 6. And also, finally, the probability of success has to remain fixed throughout all trials. So the chance of rolling a 6 being 0.2, that's got to be the same for all rolls of the dice. So just pick any 3 from these 4 bullet points and you're good. Now part B, it says, modelling now the above as a binomial distribution, find the minimum number of rolls required such that the probability of rolling at least 3 6s is greater than 90%. So what we're going to do for B is we're going to say that this distribution x follows a binomial distribution with n rolls. Now this is what we need to work out n. The probability of success is 0.2. So we want to find n, where n is the minimum number of rolls to enable this to be true. Probability of success of rolling a 6 is 0.2, which is where this 0.2 comes from here. So what we're wanting in this scenario is we're wanting the probability that this random variable is at least 3, in other words, there's at least 3 6s. We want that to be greater than 90%. So we want this probability here to be greater than 0.9. Okay, so that's how we write down the probability of rolling at least 3 6s. It's written like this. Greater than 90%, that's where this thing here comes in. Now, if you remember from chapter 6, we can only do binomial probabilities when the inequality symbol is this exact one but facing the opposite way. So I need to rebrand this. The chance of x being 3, 4, 5, 6 or higher, that's everything apart from x being 0, 1 or 2. So we can say this is the same as everything 1 apart from minus the probability that x is 2 or less. Okay, so all we've done here is just rewrote this in this form, which we can now use in a much easier way. So if we now add this to both sides, what we're going to get is that 1 is greater than 0.9 plus p x equal or less than 2. So in other words, what we want here is we want the probability that x is equal or less than 2 to be less than 0.1. So now it's a case of remembering what we do on the calculator. So we get the calculator ready. Here it is. Now we press menu and we scroll down to this bell curve. Okay, distribution. So we press equals to get into the distribution mode. Now because we're using this symbol here, not x equal to a number, but this is going to be a cumulative binomial probability hereafter. We want the probability of x being everything up to and including 2. So we scroll down and go for binomial CD. So we press 2 for variable, and so x, we want to go up to the number 2, so our x is 2. The probability of success for this dice is 0.2, probability of rolling a 6, and n, we don't know what n is. This is the question. We're trying to work out what n has to be. So we're wanting the smallest possible n such that this thing here is less than 0.1. So I don't know, let's just guess that n is 5. It's going to be a case of trial and improvement. 0.94, that's 94% chance. We want it to be less than 10%, so that's way too small. So let's go for n is 10. Still way too big. We want that to be 0.10. It's like 0.67. So let's up the stakes. Let's go for n being 20. See what happens there. Well, now we've made a big dent. Now it's come down a lot, but we're still more than double what it needs to be. So let's jump up a bit. Let's go to 23. Now we're getting close. So 0.13. That's still a bit too high. We want it to be less than 0.1. Try 24. 0.11, the next one might do it. Remember, you want the smallest possible n, so this number here goes just below 0.1. So fingers crossed, maybe it'll be 25. When n is 25, we get just below 0.1. So therefore, n must have to be 25. So that's a binomial probability question of a type you've probably not seen before in that way, but now you've seen it, now you'll know how they work. So that's the answer to 1. Let's move on and have a look at question 2. So number 2, find the resultant force acting on this object A below and indicate the direction of acceleration with an acceleration vector. So let's consider now forces going horizontally. So what's the sum of the forces horizontally? Well, we've got 3 to the left and 3 to the right, so it's going to cancel. So there's no force in the horizontal direction. However, if we consider the forces acting up and down, the resultant of the forces up and down, we've got 15 going up, which is opposite in direction but not equal to 9. 15 is bigger than 9, so the 15 Newton force will prevail. It's a greater magnitude than the 9. So overall, we're going to have 15 minus 9, which is 6 newtons going up. So therefore, the resultant force is 6 newtons upwards. And it does say as well, to indicate the direction of acceleration with an acceleration vector. Well, now we know it's accelerating upwards, I'm just going to do an arrow going upwards like so, and I'm going to draw on a double-headed arrow to show that it's an acceleration. So I'm going to label this A underscored to denote that it's acceleration, which is a vector. It's got a magnitude and a direction. It's got a certain size, the direction is upwards. Question 3 links back to question 2. So question 3 says, given that the object A from question 2 has a mass of 12 kilograms, find the magnitude of the acceleration of A. Here's where we need to use Newton's second. So we're going to use F equals ma. So from before, the resultant force was 6 upwards. We're only considering the magnitude, so we don't need to worry about the upwards actually here. So the force was 6 newtons. The mass of the object, we're told now, is 12 kilograms. So we can say m is 12. And then we're trying to work out the acceleration. So what is the magnitude of the acceleration? So now it's just a very, very simple formula. 6 equals 12a. So therefore a is just going to be 6 over 12, 6 divided by 12, which is 0.5 meters per second squared. And that's it for that question. Finally, for the warm-up, question 4. We have here a car which is accelerating from rest at a constant rate of x plus 1 meters per second squared. Until it reaches a speed of 20 meters per second, we must write down an expression for the time taken to reach 20 meters per second in terms of x. Keyword again, or keywords, accelerating at a constant rate. Okay, what this now implies, for definite, is that this is a SUVAT question. So let's just write down SUVAT. So we're interested in the time taken. Okay, so I'm just going to put t for time, because that's what we're trying to find out. So we know the acceleration in terms of x. The acceleration, actually I'll just rub some of that out, you'll explain why. So it accelerates at a constant rate of x plus 1. So a for acceleration, we can fill this in, that's x plus 1. Until it reaches a speed of 20 meters per second. Well, is this the final speed or the initial speed? Let's just consider it carefully. It says it accelerates from rest. So because it's accelerating from rest, that means it starts off with a speed of 0. We then need to think about how long it takes for it to reach a speed of 20. So the final speed we're considering is 20. S, for displacement, we don't know, we don't need to know it, we don't care. So I'm just going to put a cross against S. So which one of the SUVAT formulae doesn't rely on S? So have a little think about them, if you can. Hopefully, with a bit of brainstorming, you'll realise it's going to be V equals U plus AT. So our V is 20, our U is 0. We don't need to put 0, but I'm putting it in here so you can see that I'm using U, not just ignoring it. Then plus AT. So A is x plus 1, T is T, which we're trying to find out. So just a little bit of colour coding here so you can see where my values and numbers have come from, hopefully. Okay, so now all we need to do is just rearrange this. So therefore, T is going to be 20 divided by x plus 1. So I suppose we could include units with this. We've got meters per second, so the units of time are going to be seconds. So T equals that 20 over x plus 1, which makes sense in a way. If acceleration is greater, the denominator's greater, the time is smaller. Greater acceleration the time taken to reach a set speed will be less, because it's speeding up and getting there really fast. Okay, let's now have a look at the main part of today's session. So I must warn you, hopefully you don't get dizzy, so hang on to your seats. Ta-da! Motion in 2 dimensions. So today, this main section, we're going to look to extend the idea of using f equals ma from 1 to 2 dimensions using vector representations. So Newton's law, second law, becomes a vector equation bold f equals m bold a. So bold f and bold a denote that those two are vectors. They have a size and a direction. The normal font M, without being in bold, is just there to show that m is simply a scalar. Mass has a magnitude, but you can't have a direction associated with a mass. You couldn't say that your mass is 80 kilograms to the left. That would just be a nonsense. So obviously mass is a scalar, but f and a, force and acceleration, can be considered as vectors. And so in ij notation, we're going to say here that f is ai plus bj newtons, and a is ci plus dj meters per second squared, where a, b, c and d are constants. So let's have a look now and see if we can apply this. So let's look at this worked example. We have a particle on a smooth, flat surface. So smooth, there's going to be no friction at all, nothing else to consider, apart from these forces below. It has a mass of 50 kilograms, and it's got different forces acting upon it. So find a and b, given that the particle's acceleration is the vector minus 2, 3.2 meters per second squared. So first of all, we're told about forces and acceleration and also have a mass. This is going to be a case of doing f equals ma in vector notation. So what I could do here, in fact, is just say sigma f, the overall resultant force of all these vectors. So if we just add together these forces, we've got 600, so what did I say 600 for? 100 plus 60, I'm going crazy, and then plus minus 50 and 40, and then F3 is 2a and 3b. So adding all of these up, 160 minus 50 and 40, and finally 2a and 3b. That's going to give us the overall resultant force. So add the tops, 100, take 50 plus 2a, that's going to be 50 plus 2a. And the bottom ones, 60 plus 40 plus 3b is going to be 100 plus 3b. And so that is what the resultant force is. So therefore we can say that that resultant force, 50 plus 2a on top, and on the bottom 100 plus 3b, that equals a mass, which is 50, multiplied by the acceleration, which we have here is minus 2 and 3.2. Now we can multiply scalars with vectors. It's very much like expanding brackets, but instead of expanding it horizontally, you're expanding it vertically. So instead of multiplying the 50 by the numbers going to the right, you multiply the 50 by starting at the top, then going down. So 50 multiplied by minus 2 becomes minus 100, and 50 multiplied by 3.2 is 160. Now what we can do is consider the tops of these vectors, the I components. So the top here we had 50 plus 2a, and that must equal minus 100. In exactly the same way, this 100 plus 3b must equal 160. So from this we can deduce 50 plus 2a is minus 100. And if we rearrange that one, it's fairly straightforward. Subtract 50 from both sides, then half. We see that a must equal minus 75. And in the same way, looking at b here, we've got 100 plus 3b equals 160. So now if we subtract 100 from both sides and divide by 3, we can hopefully see that b would have to be 20. So all we've done there really is just applied F equals ma, but considered F and a, force and acceleration, as vectors. In this case we've considered it as column vectors. We could have done it in I and j components as well. It just completely depends on the context and the question at hand. Let's have a look at another worked example then. So this one, worked example 2. So we're told in this example, I is the unit vector due east and j is the unit vector due north. So first of all, we have a particle mass 10 kilograms which is at rest. It's acted on by 3 forces, F1, F2, F3. First of all, what we need to do is to find the resultant force, R newtons, in the form AI plus bj newtons. So R is just going to be the total of all these forces. So what I'm going to do here is consider the I components separate to the j components. So we have 3i, another I, and another I. So we have 3 plus 1 plus 1 lots of I, and then we have, as well as that, j components to consider as well. So the j components, we've got a minus 5j, a minus 8j, and plus 1j at the end. So we've got minus 5, minus 8, plus 1j. So if we just simplify the I and j components, which is fairly straightforward, we see that the I component here is 3 plus 1 plus 1, which is 5. So we have 5i. Then here for the j, minus 5 minus 8 is minus 13. Minus 13 plus 1 is minus 12. So I have 5i minus 12j. Part B. Find the magnitude and bearing of the acceleration of the particle. So first of all, let's try and find the magnitude. So the magnitude is just simply a case of Pythagoras. So we take each of the numerical constant components of I and j, square them, add them together, then square root. So the size of the resultant is going to be 5 squared plus minus 12 squared. So if we try this out, go back to normal mode, so square root of 5 squared plus minus 12 squared. This is a Pythagorean triple. A 5, 12, 13 triangle is a triangle with all sides whole number lengths. It's called a Pythagorean triple. So this one gives exactly a hypotenuse, a magnitude of 13. So the size of the resultant force is 13 newtons. Now we need to work out the bearing as well. So bearings are always measured clockwise from north. So I'm just going to draw on a north line like so. That's a bit wonky. I'll get that straightened out. There we go. Now let's consider the resultant force. 5i minus 12j. That means it's going 5 along and 12 down. So it's going to be this sort of direction here. It's going to be a bit along but mainly down, like so. So if we just try and sketch in now, like that. So I'm going to label this R. So it's 5 along, 12 down. So to find the bearing, what we're essentially wanting is the angle starting from north, going down and around until we hit R like that. Now I'm hoping you can see here that this blue angle is actually a 90-degree angle, like so, plus also this angle of this 5-12 triangle as well. So what I need to do here is do 90 degrees plus this purple angle here. So this purple angle, think of it in terms of trigonometry. I've got this triangle here at the bottom. Opposite to this purple angle is 12, and the adjacent is 5. So the bearing is this 90 degrees plus this angle here. Because we know the opposite and adjacent, we can find the angle using tan, but of course it's going to be tan minus 1 when finding angles. So it's going to be tan minus 1, 12 over 5. So let's work this one out now. So just get the calculator ready and we should have it. So we've got here 90 plus shift, tan minus 1, 12 over 5, and that gives us a total angle of 157. Now you need to recall, bearings are 3 digits, and if you don't have enough digits, you start with zeros. So what we're going to do here is just call this 157 degrees. Finally, part C, find the distance travelled by the particle in its first 3 seconds of motion. Now this question here, we've got these forces F1, F2, F3, which gives us resultant. There's nowhere in the question to tell us that these forces are going to be changing, so we can assume that these forces will be constant. So constant forces means constant resultant force, which means constant acceleration. And so this one here is actually a Suvat question. It's a Suvat question dressed up. It's not obvious because we don't know much initially, but actually what we do know now is the resultant force, and we know the particle's mass. So first of all, we can apply F equals ma. Resultant force is 13. Mass of a particle is 10. And the acceleration we can now work out. So 13 equals 10 times a. Therefore, the acceleration of this particle is going to be 1.3 meters per second squared. So we can now add in Suvat. So what we're trying to find here is the distance travelled by the particle. So I'm going to label S as S because we want to find S. We're also told at the very beginning that this particle is at rest. So the initial velocity is 0. We've now worked out the acceleration of this particle. This acceleration is 1.3, so I can label in 1.3. And as well as that, we've been told it's a distance travelled in the first 3 seconds of motion. So the time we're using is 3. The final velocity, we've not been asked to work out. We don't know it. So, to be honest, we don't really care. So I'm going to put a cross against v just to denote that we don't really give a damn. So what we need here is an equation of motion, a Suvat formula, which doesn't rely in any way on v. So again, it's our old favourite. It's s equals ut plus half at squared. So if we just plug in these numbers, so u is 0, so we've got 0 multiplied by 3. You might be thinking, why am I bothering to write this in? It's just for completion. With practice and experience, you can be confident enough to just ignore this altogether. I'm just trying to show you it step by step. Then we're going to do plus a half multiplied by a, where a is 1.3. And then we're multiplying that by the time, which is 3 squared. So all we need now is our trusted calculator. So 0 times 3, I'm not even going to bother with that one now. I'm going to jump straight into doing a half multiplied by 1.3 multiplied by 3 squared. And that gives me 5.85 meters. And that's it for that question. So now, as you might have guessed, or dare I say feared, it's now over to you to try some of these on your own. So, on page 167, you'll find exercise 10D. I'm liking you now to have a go at questions 1, 2, 4, then 6, 7, 8, 9 and 10. Check your answers as you go, as ever. If you get stuck, ask a friend who sat next to you or try and work out where you've gone wrong yourself. If you're still not sure, that's where I come in. So you know how to find me by now. I'm not going to mention again. Look back on one of the old videos. So thank you very much for listening and getting to the end of the video. It is appreciated. Consider subscribing, that'd be really nice. Take care, and I'll hope to see you soon.